morning, everyone. I'm Jiabin, a PhD student supervised by Dr. Tian, working on the application of high-temperature superconductivity. I appreciate the opportunity to be with you today. I'm here to talk to you about our research on a wireless power transfer system using high-temperature superconducting capacitors. There are 5 parts in the presentation. We are going to look at the introduction, methods, results, summary, and future work. There is time for questions at the end of my talk. The wireless power transfer system, referred to WPT system, has different types. Non-resonant coupled inductors, such as transformers, work on the principle. Non-resonant coupled inductors, such as transformers, working on the principle of a primary coil, generating a magnetic field, and a secondary coil subtending as much as possible of that field. This can happen only in a short range and often requires a magnetic core. In contrast, the wireless power transfer here means to transfer energy in a resonant inductive coupling way. Resonance coupling forms a tuned LC circuit. Significant power can be transmitted with a primary coil driven at a secondary side resonant frequency. Meanwhile, this type of wireless system's efficiency depends on the quality factor of the inserted resonant circuit to a large extent. Correspondingly, high-temperature superconductors, also known as HTS tapes, are promising candidates to overcome this challenge due to the almost zero resistance. Most relevant studies aim at applying a superconducting coil in the electrical system because it can carry significant current density and create a strong magnetic field. But few studies the effect of a superconducting capacitor with a relatively higher dielectric constant in the substrate layer. Therefore, we proposed that 2 high-temperature superconducting tapes holding substrate layers together can also be fabricated to a high-quality capacitor with much lower power loss in cooled superconducting thin films and substrate. Now let's move on to the methods. Our research starts from modeling, and we presented in February's middle project meeting. We have further revised some of the data, and today we are presented with the experiment together. By the finite element method, we simulate the coils and capacitors based on the actual geometry and materials. Coils are simulated using 2D axial symmetric modeling in CAPA multiphysics. Normal coils are made of copper wire. Superconducting coils are made of superconducting tapes. Inductance and the equivalent series resistance, the so-called ESR, at high frequencies are predicted. Figures illustrate the photographs of coils assembled from copper materials and superconducting tapes and their appearance in the finite element package. Likewise, capacitors are simulated using 3D modeling because the area of the electrode plates affects the capacitance. Control group capacitors are made of copper as electrode plates and ceramic as dielectric. Superconducting capacitors are made of HTS tapes. We measure the capacitance and ESR at high frequencies as well. In addition, the vector network analyzer, so-called VNA, is served as a measuring tool for inductance and capacitance. Next, the wireless power transfer system's equivalent circuit is developed in MATLAB Simulink, and the modeled inductance, capacitance, and ESR are used as the inputs of the circuit. The voltage transfer efficiency can be correspondingly calculated. In terms of the system experiment, the setup schematic is shown on the left half. The transfer efficiency is measured using a vector network analyzer as well. Specifically, the right half shows the combinations of coils and capacitors, normal coils plus normal capacitors, superconducting coils plus normal capacitor, and superconducting coil plus superconducting capacitor. 3 cases are all tested as a resonant circuit in the wireless transfer system. It is worth noting that the superconducting materials need to be immersed in the nickel nitrogen bus, and that is why there is a cryogenic container in Figure 7. Let's turn to a results discussion. The two tables list the simulated and measured results of coils. We can see their corresponding inductance and ESR basically match. More importantly, the superconducting coil has a much smaller ESR than the normal coil. At the same time, the capacitance and ESR measured in the experiment is consistent with the simulation. And the superconducting capacitor also has a much smaller ESR than the ceramic capacitor. Therefore, under the same inductance and capacitance, both the superconducting coil and the superconducting capacitor have much smaller ESR than the conventional components, meaning there is a higher quality factor in the superconducting resonator. Then, Figure 8 plots the simulated voltage transfer waveforms of the system assembled by the mentioned different resonator cases. We calculated the ratio of the amplitude of the input voltage and the load voltage. We can see the superconducting coil in the resonator can improve the efficiency from 45% to 55%. And the superconducting coil working with superconducting capacitor further increased this figure up to 70%. That is to say, the addition of superconducting materials can gradually improve the transfer efficiency. And the resonator consisting of a superconducting coil and a superconducting capacitor performs best at a resonant frequency. Furthermore, we curved the transfer function expressed as a scattering parameter, namely the S parameter, which describes the input and output relationship between ports in an electrical system. Different combinations of in the resonator are tested in simulation and experiment, respectively. Both simulation and experiments show that the resonant inductive coupling WPD system is most effective at a resonant frequency, and the all superconducting resonator exhibits the highest transfer efficiency. The deviation of simulation and experiment may be due to the insufficient accuracy of the coupling coefficient in models and data collection methods. The troughs that appeared in the experiment did not appear in the simulation. The reason is that in the simulation, each frequency is simulated separately and discrete points are connected. However, the experiment was to directly sweep the system with a specific frequency range in the vector network analyzer. To summarize, our research consists of two parts involving simulations and experiments. First, the inductance, capacitance, and ESR of the coils and capacitors at high frequencies are examined with the help of finite element method. Material type, geometry size, and transmission frequency are all considered. Then, the wireless power transfer system model has been developed to estimate the transfer performance. The transfer efficiency of different resonant materials at frequencies is calculated, showing the significance of superconducting materials. Besides, based on the model parameters, coils and capacitors are fabricated. The assembled wireless power transfer system works and once again proves the effectiveness of superconducting components. In general, the measured results agree well with the simulation. Finally, future work continues. The superconducting coils have consumed considerable superconducting tapes and show non-negligible AC loss at high frequencies. The follow-up work is to achieve a more economical coil through an optimized tape structure. For example, the thickness of the layered structure of superconducting tapes can be used to adjust the resonant frequency. Also, we have to note that a capacitor has an electric field limit known as a breakdown voltage. So the next focus should be on the dielectric strength of the superconducting capacitor to avoid a short circuit fault in the resonator. As for a system, due to the limited time during the COVID-19, we did not implement a real power supply. Therefore, we plan to experimentally install a power supply and load to monitor the actual transfer efficiency and charging speed. Well, this brings me to the end of my presentation. Thank you for your attention, and thank you to all the staff who are working during these challenging times. I would be happy to answer any questions you might have.
Thank you very much, Jiabin. Yeah, this is an excellent coverage of what you have done, and it's totally understanding in the COVID situation, the lab access is restricted. But nevertheless, what you showed here is very promising. The talk is now open to questions. Is there any questions? You can unmute your mic to ask.
Yes, please, Professor Chu.
Thank you, please.
Hi, Jiabin, thanks, good presentation. Of course, with any superconducting implementation, we're always interested to know how hot can it run? How much do we need to cool it in order to get good efficiencies? Where's the sweet spot between the expense of needing to do the cooling and the benefits from the increased efficiency?
Okay, thank you, Michael. It's a very good question. What we used is high temperature superconductors. So they should be immersed in liquid nitrogen. So the temperature is just 77 K. It's around minus 20 degrees. But for the low temperature superconductors, the temperature will be very, very low and very, very expensive. So that's the advantages of high temperature superconductors. In terms of the expense, I would say liquid nitrogen is relatively very cheap. I think the price is as equal as water in the supermarket. So I think that's fine. Yeah. But the temperature we need to pay much more attention, because when the transport current is higher than the critical current, so the quench occurs, it may burn out the superconductor. So that's a very critical issue in the application of superconducting materials. Yes, that's it.
Thank you.
Thank you.
Thank you. Any other questions? Jiabin, I have a quick question. You showed the improvement of the efficiency, etc. What do you think any further improvement can be made? And does that including using the wiring, use the high TC superconductors in the wiring as well? Because the part that you focus so far is mainly on the capacitor itself.
Yes, I would say, like what I mentioned in our future work, I think we should do more work in the HTS coils, because the superconductor only shows zero resistance in the DC current. So when the frequency of the current is very high, the AC loss is considerable. So we should try our best to minimize the loss in the HTS coils. So I think this is the first point. But by the way, actually, the structure of HTS coil is customized. So like we can reduce the use of copper and silver in the superconductors to reduce the eddy current loss, etc. Another point in terms of our work, I think we should increase like the materials, I would say magnetic core or kind of thing in the system to increase the efficiency, because we just want to compare the difference with or without the addition of superconducting materials. So we didn't use any magnetic core or kind of thing. I think later we should consider this point.
So you're talking about the flux pumping technique.
Yes, we will see.
So, Another question is how high the current density you can achieve nowadays. I think that will limit how much power you can transfer.
Yes, actually, first in our experiment, we didn't imply a real power supply due to time, but we will do it later. But the question depends on the performance of superconductors. What we use, the critical current is just around 200 amperes. So, but it depends. If we need to increase the power, of course, we need to use a kind of new superconductors. So I think, yes, we need to keep the current much lower than the critical current for the safety issues.
Yeah, I was wondering because the people are aiming for kilowatts or higher, and of course the current is a limit, but maybe you can increase the voltage or whatever the things. Yeah, try to
yes
power high.
Yes, it is. Yeah, and we can increase the number of coils maybe. Yeah, because we just use a single pancake coil. Maybe I use double or something. Yeah, we'll see.
So you think that the approach you are doing is scalable to the high power?
I expect that, but I need to do the experiment to see how it gets around.
Sure, sure. At least there is no fundamental barriers for it.
Okay, thank you.
Okay, thank you very much. Any
Thank you.
questions? Okay, if there's no further questions, let's thank Jiabin for the excellent talk.